Howdy folks. In this video we are going to get an introduction to stochastic modeling, and I'm going to assume that you understand some of the basic principles behind stochastic modeling, and so we're going to do a set of exercises that illustrated in this list here that's found on our class webpage to learn how to set up and run a stochastic simulation inside GMS. We're going to do both just standard Monte Carlo, and also we're going to do that with parameter randomization, and we're also going to do a Gaussian simulation, and then we're going to do a probabilistic capture zone analysis. So there's a stochastic.zip file that you download and unzip, and I've already done that, and I've got a version 2 of this I'm going to use here. So when you open this up, you will see that it includes our familiar Big Valley set. Let me change the background here, and let's see, to better illustrate what we have here, I'm going to go into the contouring options, and I'm going to use a color ramp here. And so now I'm going to expand this a bit. And so as you can see, let me turn off those cell edges a little bit. So here's our groundwater model. Now, this is the same one that we covered in our other exercises where we did the model calibration and automated parameter estimation and pilot point interpolation and things like that. And so this model has already been calibrated. Now if you go back to, let me turn the grid off for a second, and let's just go in here and look at, here's the recharge coverage, and if I look at this, and if you look at, we have a series of polygons, each of which has a key value, meaning it's been parameterized. Same thing with hydraulic conductivity. I turn that on. Let's see, let me just select all of them. Go to the attribute table, and you'll see we have these different parameter zones. I guess another way to look at that is you could double click on this HK array, and you'll see these key values, and we have the set of parameters listed here in the parameters dialog. Excuse me, that's popped off the screen here for a second. And so we've already done the automated parameter estimation using zones, and we've imported the optimal values, which are shown here as the starting values, and it's been switched back to a forward run. And so what we're going to do is we're going to convert this to a stochastic simulation. Now, when you do a stochastic simulation, you have to parameterize your input just like you would for automated parameter estimation. And that allows us to indicate what parts of the input we want to parameterize, or excuse me, we want to randomize, and to control how that randomization takes place. And so we are going to go into the, let's see, let me go back to the head solution. And as you, again, if I click on the, hang on just a second. Having a hard time, oh, excuse me, observation wells. I was clicking on the wrong one. So here's our observation well. So this has been calibrated. If you look at the properties, you'll see there's all of our residuals are really small. The sum of the squared weighted residuals is small. So we have a calibrated model, but now we want to do a stochastic simulation so that instead of having a single best answer, we're going to have a range of model instances, each of which we consider to be equally probable. And then you can use that to run whatever scenario you're concerned with and determine a probability that some event is going to occur. So the next step is to go into mod flow global options, and in the run options change it to stochastic. And there are some stochastic options here. We're just going to stick with basic parameter randomization. And the next thing we do is we go to the parameters dialog, and we tell it that we want to randomize each of these different parameters. And so the value that's shown here becomes the mean value. Now notice at the bottom of this dialog it makes a list of our model instances, and let me adjust this a little bit, and we're going to log transform everything, and we're going to randomize each of these. So every time I click on one of these, it adds it as a column. So each parameter is a column in this list at the bottom. And I'm going to switch this from Latin hypercube to random sampling. And then over here in the number of model instances, it defaults to 1. But whoops, I hit the return key and it exited the dialog. I'm going to change that to 30. And when I do that, let me see if I can widen this a little bit. There we go. When I do that, it populates this table from run 1 to run number 30. So basically, each of the rows in this table represents a separate model instance. So for run number 1, for my parameter HK200, it's going to put in a value of 0.0014. For HK100, it'll be 3.56, 300 and 0.826, and so forth. And then run number 2 will have its own set of values. Now these numbers in this list are generated using probability distribution function, just assuming a normal, actually a log normal distribution. And again, the mean value that it uses is pulled from my list up here. But there's also a standard deviation. Now, if you're doing just if you're not log transforming the numbers, then the standard deviation is just what a normal standard deviation means. But if it's log transformed, you have to remember that the standard deviation represents like the number of log cycles. And so 1.95, that's just a default that's thrown in there. But we're going to change this to 0.3. And you know, where did I get that number? Well, I've experimented with this problem in the past, and that tends to work well. So this is 0.3 log cycles is my standard deviation. And when you do that, you get a little bit tighter range down here. Now, by the way, there's a histogram button, and for each of these you can generate a histogram. Now, we only have 30 model instances, so we don't get a very well-defined histogram. But what if I change that to 300? And now I've got 300 model instances listed here. Now, when I click on the histogram, you'll see it more closely resembles what you'd expect for your PDF. And let's go up to 1,000. Why not? Doesn't take very long to generate, and the more you have, the more closely that resembles a well-defined normal distribution. So let's see, those are biased to one side. That has a really small number, so that one ends up being kind of biased because the mean is really small. Oh, actually, it's not that small. I'm not sure why that one is biased over to the side. And by the way, if you click repopulate runs, it generates a new set of values for you. Oh, let's see. If you look up in the, I know why this one is off, because if you look up in this list, it has a min and a max, and for some reason the min for this parameter is set to a higher value. I'm going to change that to match the others and tell it to repopulate the runs. And okay, there we go. Now we get a normal one. So basically what was happening was the min was set equal to its standard value. And so I was only getting half of the PDF. So I'm glad I checked that. We need something I need to fix there. And again, every time you hit repopulate, it generates a new set of values. And by the way, if you want to, you can select user defined, and then you can paste a set of values in here from from a clipboard. Maybe you have your own logic you're using in an Excel spreadsheet to generating your parameter values, and there's an Excel add-on called Crystal Ball that's the whole point of it is to generate randomizations associated with Monte Carlo simulations and stochastic simulations. So there are some more sophisticated tools you can use out there to do that, but this is one way to do it. Now another method for doing this is instead of random sampling and telling how many instances you have, you can do a Latin hypercube method. And with this one, instead of telling it the number of model instances, we tell it the number of segments, or these are like quantiles. Probably quantiles would be a better name for it. And it basically, when it generates its model runs, to do that, it breaks up each. If I put I'm using 3 quantiles for each one, so it generates 3 quantiles in the PDF in the probability distribution function, and they're spaced so that the area under each of those 3 segments is the same. So they each have an equal probability, and then for each model instance it generates a random value for each of those, but it does it so that it combines these quantiles. So the first time it would say generate a number in the first segment for each of them, and then for the second one it said, okay, for the first one do a number in the second segment and the rest of them in the first segment, and then do one in the third segment and the rest in the first segment. Then now do this in the first segment, the second one in the second segment, and the rest of them in the first segment. So it finds all combinations of sampling from the different segments. And so your number of model runs is equal to the product of this row of numbers here, 3 times 3 times 3. 3 to the 1, 2, 3, 4, 5, 6, 3 to the 7th, which gives you 2,187 for this particular set. And again, you can repopulate your runs there. And the theory behind Latin hypercube method is that you're still doing a simple Monte Carlo simulation, but it gives you, it ensures that your parameter space is more uniformly explored, and so you can get a better confidence in your answer with a lower number of model runs. So that's an option. So we're going to go back to the random sampling, and then we don't have time here to do 1,000, so I'm going to change that to 30. Now I got to be really careful. I'm only doing 30 because we want it to go quickly. I would never dream of doing a stochastic simulation with only 30 model runs. You can't really have much confidence in your answer with only 30 model runs. I often have students do a stochastic model on a term project, and they end up doing 30 model runs because that's what we do in this example. But I would do at least 300, and I'd do as many as you can get away with. But we're going to keep that at 30, and then we're going to do save as, and we're going to call this let's see, Monte Carlo -1.gpr, and then we're going to run. And what it does is it builds a table of each of your model instances here, and it runs those. Now you got to remember that we're randomly so we're perturbing each of these parameter values around its mean. It's going to be concentrated at the mean, which we found through, it's the optimal value we found through automated parameter estimation. But then it's going to perturb it using the standard deviation we defined in a PDF, a normal distribution. And it could be that if you have your standard deviation too high, it's possible that you could get maybe a low value of hydraulic conductivity that ends up causing part of your aquifer to go dry or something. And so it's possible that when you do this, you can have combinations of parameter values, maybe a high conductance and a low recharge or something that would cause your model not to converge. And so we keep track of that. And in this case, they all converge, and I picked the parameters so that they'd be well behaved. But sometimes some of them will not converge, and so you need to be aware of that. And then in this dialog, it allows you to, if we had some that hadn't converged, they would be unchecked, and we can choose not to read them in. But we're going to go ahead and read all of these in. So what it does now is it reads all 30 of those simulations into memory, and they're listed here in this folder. And I'm going to highlight the first one, and I'm going to use the down arrow on my keyboard, and I'm just going to kind of cycle through there. And so what you're seeing is the solution computed by each of these individual model instances. And so the manner in which we've done this means that each of these model instances is equally probable, and because of the way we set it up. But some are going to have, some are going to deviate more substantially from our calibrated solution. And so if you wanted to look at how, what kind of error you get, I mean, this one has 434,000, some of the squared weighted residuals. And let's see, this one is 28 million. Interesting, because it has a big flow residual. And so, well, that's interesting. That one has, well, that's got to be a bug there. That doesn't make any sense. Oh, because let me try it again. Maybe it wasn't fully selected. And anyway, we look at the mean residual for head and for flow. I mean, those individual error norms aren't that bad. But there's some difference. But the bottom line is these are all considered equally probable, and we could go ahead and do some sort of probabilistic analysis. And so, maybe you're looking at your flow budgets, and there's some threshold value you need to be concerned with. And so you would say, well, for example, if my flow budget met a certain target on 25 of the 30 runs, or excuse me, let's say 20 of the 30 runs, I would say, okay, then there's a 67% probability that this will occur. And so, it just depends on what it is you're analyzing and how you want to interpolate that or interpret that. But that's one way to do it. And so let's shift gears now and do a Gaussian simulation. Now, a Gaussian simulation is a little bit different technique. Instead of using these parameter zones that we've defined, we are going to define a Gaussian field defining our hydraulic conductivity and how it varies over the domain of this model. Now, a Gaussian field, it's kind of like Kriging, the interpolation technique. And if you have some, if you're doing hydraulic conductivity, if we had some points in this model domain in the aquifer where we'd measured the hydraulic conductivity, it would basically interpolate those, but then between those it would generate some artificial heterogeneity. And so it allows you to generate a set of hydraulic conductivity or recharge fields which exhibit a certain amount of heterogeneity, but it's perturbed about a mean once again. And so and when you introduce heterogeneity, it's a good way to deal with things like travel time analysis or capture zone analysis, because the underlying aquifer really is heterogeneous. It's not nearly as smooth and uniform as we often portray it. And so we need a 2D scatter point set. So I'm just going to create, right-click and select 2D scatter point set. And we can right-click on that and rename it to Gaussian points. Now, if we had some existing points, we would import them into this scatter point set, and those would be used to condition our Gaussian fields. But you can actually do Gaussian interpolation without any existing points. You just have to define a mean hydraulic conductivity for it. And so with that selected, I'm going to go to the interpolation menu and select Gaussian simulation options. And we're going to do log interpolation. And we are going to do 30 realizations once again, and we need to define a variogram, and we are going to use a nugget of 0, a contribution of 0.3, and a range of we want to do 700 to 1,000. Let's do 850 here, kind of split the difference. And that defines our variogram. Now remember, a variogram, so 850 means that the lens length, if you have, connected faces or lenses in your hydrostratigraphy, that they're about 850 feet or meters long on average. And you can vary that, and then the contribution is kind of your variance, your semi-variance, your average semi-variance once you get outside the correlated distance where you have your range. So I'm going to click OK there, and let's see, we want to truncate our values between 0 and 200. We want to kind of limit that. We don't want anything negative. I'm not sure 0 is a really good value. We'll make it something that's a little positive. And we'll click OK. And then we'll select Run Gaussian Simulation. And it, mean field crashed. That's interesting. Let me try that again. Let me change that back to 0. Maybe that was a problem. It's a little bit different than what I ran earlier. Mean field in zone with, let's see. Mean field values within each zone are now requested. Mean field in some integer value 1. Okay, let me dig into this. Okay, I figured out I missed a very important fundamental step. If I go back to the Gaussian simulation options, I don't have any points to condition to, so I need to enter a mean value, and I entered it, and I left it at the default value of 0. We want the mean value to be 0.4. I'm going to go ahead and put this back to what I had before. So that's the problem. You can't have a mean of 0. So let's try that again, see if we get farther. Sure enough, it's working now, so that was the problem. And now what happens is it generates this folder of these arrays. These are basically data sets, just like simulated head fields or something. And you can see it's done on, it did the interpolation on a log scale. So you have these little pockets of variation. Now, in order to, since it's interpolated on a log scale, we want to go into our interpolation, or excuse me, our contouring options, and change this to do log contouring. So the way that you do that is you click on specified values, and you tell it to populate values, and you click this log scale option here, and it generates a series of intervals corresponding to a log scale. So now, as I cycle down through here, you can see the heterogeneity that it's defined. As I move my cursor through here, you'll see the hydraulic conductivities vary from 0.01 up to, let's see, this one's at 14 or 15. And let me go to the next one. We got a pocket down here at 30. Anyway, so the lengths of these, you can see these little zones that it's defined representing kind of contiguous values. They're within a certain range. So these are, the size of those is based on the range we had in our variogram. And how much it varies is based on that contribution value, or the height of that variogram. And where did I get those numbers? Well, I experimented until I found something that looked good for this particular data set. But there's a lot of literature out there that would educate you on how to do this most properly for groundwater modeling and hydraulic conductivity. But the point is, we have these this set of data sets which we could now use as our hydraulic conductivity values. And so I'm going to collapse that for a second. And to do this, I'm going to go into my HK array, and I'm going to change everything to a -100. So I want all of my hydraulic conductivity to be a single parameter. And I'm going to go into my parameters dialog, and I'm actually going to delete my other hydraulic conductivity parameters because all I have now is HK100. And I'm going to turn on this use multiplier arrays option. I'm going to tell it to use multiple arrays, and I'm going to pick my that folder that has my Gaussian simulations. And so basically what it does is, for my hydraulic conductivity property, it populates that using that folder of Gaussian fields. So every time you do a model run, it's going to pull in one of those Gaussian fields and plug it in for hydraulic conductivity, and then it's going to do your normal stochastic randomization, use a normal distribution, or excuse me, a log normal distribution on each of the remaining recharge arrays. So let's try that. Let's do file save as. We'll call this Monte Carlo 2, and we'll run that. And that should run fairly quickly, about the same amount of time it did before. And again, it'll tell you whether or not each of these fields is converged or not. Oh, one of those didn't converge. Interesting. Look at that. Run number 15 did not converge. And so when we click close, it will say failed. We'll just omit that one and read in the rest, and let's see what that looks like. Well, the contours don't look good, but let's go back and change that to a number of contours instead of the log interval. And so there's our contours, and now as I cycle down through here, you'll see that got the same general shape of the contours we had before, but you'll notice how irregular that looks, and there's this wiggles in our head contours because of that underlying heterogeneity. And again, this allows you to introduce some artificial heterogeneity into your system that is hopefully consistent with what you would expect based on the field conditions at your site. And so that's another way to do it. And so now that we have a couple different Monte Carlo solutions, I'm going to show you one last thing. I'm going to right click on this one and select risk analysis, and we're going to do a probabilistic capture zone analysis, and I want it to distribute particles on water table surface, and I want it to stop in cells with weak sinks. I want it to weight results based on residual error. And what it's doing now is it's going to load each of the solutions in this folder that I selected, and it is going to, once it loads it, it's going to start a particle at the center of every cell and track it to see if it ends up in a cell containing a well. And if it does, it marks that as being captured. And it does that for all of my simulations. And then at the end, it for each cell, it calculates the probability of capture. And so here's at the bottom of this folder, you'll see this 0.1, 0.2, and 0.3. So this is point number 1. And let me show you another trick here. I'm going to go in here and tell it to go from, let's see, change my lower limit to 0.1, turn off the fill below, and this will basically restrict the contouring to this region right around my well. So here's my here's the probabilistic capture zone for this well, and if I zoom in, so basically if it's inside this red zone, it means it has almost 100% probability of capture, but then it varies as you go out. You can look at this F value down here under the cursor, and I get out here and there's like a 20% probability of capture. And so what that means is the particles that were started out here In this case, about 30% of them ended up being captured, and so it has a 30% capture probability. And so this is a really nice way to analyze your capture zones. Instead of having a single capture zone, you can have this contouring of the probability of capture, which is a nice way to do it. And let's see, I'm going to zoom out. We'll pick point number 2 over here. And finally, point number 3, which is right up here. Interestingly, we got a couple over here that end up being captured. And so, I mean, we could do this that was with our Gaussian fields. You could do the same thing with our other one as well, using the same approach. But anyway, there's your introduction to running stochastic models in GMS and doing probabilistic capture zone analysis. By the way, these contours here are a little bit irregular. The more model instances you use, the smoother and more uniform that will become. But when you only have 30 model instances, things get a little bit more random. And so again, you want to do as many model runs as you can get away with. We kept it low in this case just so that we could get through this in a reasonable amount of time. But there's your introduction to stochastic modeling in GMS.